In section 3.5, we will cover limits at infinity. And our goal is to be able to evaluate limits at infinity, to be able to find horizontal asymptotes, and determine when we have infinite limits at infinity for a function. So when we're talking about limits of infinity, we are considering end behavior of a function. So we're saying, what is the function doing as x gets really, really big or really, really small, as it increases or decreases without bound. So we're talking about what is happening to the function as x gets really large, as x approaches infinity, or as x gets very small, as x approaches negative infinity. Mind you that in order for us to talk about these limits, x going to infinity or x going to negative infinity, the domain of the function also needs to go to positive infinity or negative infinity. So a quick example of what I mean by that is if you consider the square root function, which we know its graph looks like this, I could not talk about the limit as x goes to negative infinity of the square root function because the graph doesn't exist over here as x goes to negative infinity. So this limit simply would not exist. Let's look at an example of an infinite limit, a limit at infinity that would exist. So here we have a rational function. If we look at the graph of this rational function, when we talk about the limit as x approaches infinity, we're talking about, well, what is the function doing as x gets larger and larger and larger? So as you get on the graph and move to the right. Well, as we get on the graph and move to the right, it seems as if we are leveling out at 3. So the limit as x approaches positive infinity is equal to 3. And to find the limit as x approaches negative infinity, we would get on the graph and move smaller and smaller and smaller x values as x goes to negative infinity, moving to the left. And as we move to the left, again, the function is approaching the y value of 3. When we're answering these questions for what these limits at infinity are, we're asking what y value is the function approaching as x gets very, very large or as x gets very, very small. That is what we look at if we're looking at the function graphically to determine the infinite limit. We could also look at the function numerically to determine the infinite limit. Numerically just means that we look at a table. Looking at a table, to find the limit as x approaches positive infinity as it increases without bound, I would plug in x values that are getting larger and larger and larger. So maybe next I would plug in 1,000 if I wasn't convinced yet, 10,000, so on and so forth. Similarly, to find the limit as x approached negative infinity as it decreased without bound, I would plug in x values that were getting more and more negative. So maybe next I would plug in negative 1,000 to help determine that that limit is approaching 3. Because again, what we're looking for is what are the y values doing as we plug in these x values. And in both cases, we can see that these y values are getting closer and closer to 3, just as we were able to see on the graph. Now we will shift our attention to talk about horizontal asymptotes. Here we have a formal definition of what a horizontal asymptote is. The line y is equal to L is a horizontal asymptote of the function if either the limit at negative infinity or the limit at positive infinity is equal to L. So a quick example of that, looking back up here, we saw that for this rational function, f of x is equal to 3x squared over x squared plus 1, both the limit as x approached negative infinity and the limit as x approached positive infinity were equal to 3. According to this definition, we could then say that this function f of x has a horizontal asymptote of y is equal to 3. Next, we have that the properties of limits at infinity are the same as the properties of regular limits that we discussed earlier in this course. So if you think back to the sum property, the difference property, constant multiple property, the same way that we handle limits as x approaches a constant value is the same way that we handle limits as x approaches a positive or a negative infinity. We can still apply those same rules. The next theorem is going to help us evaluate limits at infinity for rational functions. This theorem says that if you have a real number c, so the numerator is just a number, and in the denominator you have x to the r, where r is a positive rational number, that limit goes to 0. And if we think about it, that makes sense because the numerator is staying constant and the denominator is getting very, very large. And as your denominator gets very large, your fraction gets very small. It goes to 0. Second part of this theorem says that the same thing happens as x approaches negative infinity, but you have to be careful and make sure that the function is defined when x is negative. Kind of like how we talked about here earlier with the square root function, not defined when x is negative. Let's look at example 1. We have the limit as x approaches positive infinity of 5 minus 2 divided by x squared. The difference property of limits that still applies to limits at infinity tells us that we could break this up into two separate limits. Notice that I did keep the limit as x approaching infinity the same on both of those limits. The first limit is a limit of a constant. That limit is simply going to be equal to that constant. We already knew that. If we're approaching infinity of 5, well, 5 is not changing no matter what x is doing. For the second limit here, we're going to apply theorem 3.10. We have a constant in the numerator, and in the denominator we have x squared that is going to be getting very large as x goes to infinity. And as the denominator gets large, the entire fraction will go to 0, leaving us with this limit being equal to 5. Example 2, we will find the limit as x approaches infinity of this rational function. First, note that if we were to apply direct substitution per se, the numerator, what's happening to the line 2x minus 1 as x gets very large? Well, that line is shooting up to positive infinity. The denominator is also shooting off to positive infinity. This is an indeterminate form, which means that it doesn't tell us anything about the limit, and so we're going to have to manipulate it to be able to evaluate it. So I'm going to begin by first taking the numerator and the denominator and dividing by x. So I've taken the numerator and I've divided it by x, and I've taken the denominator and I've divided it by x. Why am I dividing it by x? Because generally speaking, I'm going to come in and divide the numerator and the denominator by the highest power that showed up in the denominator originally. So when we look at this denominator, the highest power we see is x. So I come in and I divide everything by x. If we do that, we're truly dividing each term of this fraction by x. So I'm going to take this 2x and divide it by x. The x's will cancel and just leave me with a 2. Then subtract. I'm going to take this 1 and divide it by x. I can't simplify that, so that's a 1 over x. Moving on to the denominator, I'll take this x and divide it by x. That leaves me with a 1. Then we have a plus sign. Then we'll take this 1 and divide it by x, and that leaves us with a 1 over x. So the reason that we come in and divide by the highest power that showed up in the denominator is because it leaves us with this expression where now we have these terms that we're able to apply this theorem to. Now we have terms with a constant in the numerator and x to the power r that is some positive number in the denominator. So that theorem tells us that these two limits go off to 0. So this is equal to 2 minus 0 divided by 1 plus 0, because we know that the limits of 2 and the limits of 1 are not going to be changing, and so this entire limit is equal to 2. So when we're evaluating a rational limit and we start off and we get an indeterminate form from direct substitution, the first thing we do is we're going to come in and divide everything by the highest power of x that shows up in the denominator. Because doing that is going to allow us to then come in and apply our theorem that sends certain terms to 0 and leaves us with a limit that we are then able to evaluate. We do have some general guidelines for finding the limit at positive or negative infinity for rational functions, and they come from what we learned in pre-calculus. If the degree of the numerator is less than the degree of the denominator, then the entire limit goes to 0. That makes sense because that means that the denominator was more, and a larger denominator means a smaller fraction. How small? 0. If their degrees are equal, if the degree of the numerator and the degree of the denominator are equal, then we take the ratio of the leading coefficients. So for example, if we had the limit, I'm just going to make up a quick example to illustrate that. If I have the limit as x goes to infinity of 7x squared minus 3x plus 4 divided by negative 5x squared plus 9, I'll say. The degree of the numerator and the degree of the denominator are the same, and so we look at the ratio of the leading coefficients, which would be a negative 7 over 5. It doesn't matter if you stick the negative in the top or the bottom as long as it's there. And then finally, if the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. That does not mean that you simply write does not exist. It's either positive infinity or it's negative infinity, and we have to determine which one. Let's look at example 3. I'm going to add in a second example here. First example here, we're looking at the limit at infinity of a rational function. So I'm going to go to my guidelines. And in this case, the degree of the numerator is less than the degree of the denominator because the numerator has degree 0 because there is no variable x in the numerator, and the denominator has degree 2. Whenever that happens, the limit is equal to 0. I'm simply going to write that the degree of the numerator is less than the degree of the denominator. The second example that I'm going to make up is I'm going to look at the limit as x approaches negative infinity of x cubed plus 5 divided by x squared minus 2x plus 1. I start this off and apply direct substitution. The numerator would go to negative infinity because x is going to negative infinity, and as x gets very small on x cubed, the graph goes to negative infinity. And the denominator would go to positive infinity because as x gets very small on x squared, the graph shoots up to positive infinity. And notice that I'm really only paying attention to what these first terms are doing because these terms are going to take over. At the end of the day, these terms over here aren't truly going to matter as much. And we've seen that illustrated because we know that we can come in and divide everything in this by x squared. And I'm dividing by x squared because that was the highest power of x that showed up in the denominator. Same concept that we applied over here. And if I simplify that, I'm left with the limit as x approaches negative infinity of x plus 5 over x squared divided by 1 minus 2 over x plus 1 over x squared. And we know that several of these limits are going to go to 0. So all we will be left with is this x over 1. And the limit as x approaches negative infinity of x is negative infinity. In example 4, we are going to look at a function that has two horizontal asymptotes. And in order to do that, we're going to consider what the limit of the function is as x approaches positive infinity and as x approaches negative infinity. In both cases, well, at least in the first case for sure, if we were to apply direct substitution, we would get an indeterminate form. Because as x goes to infinity in the numerator, we would get infinity, and as x goes to infinity in the denominator, we would also get infinity. In the second case, if we apply the limit as x goes to negative infinity in the numerator, we would get a negative infinity. If we apply the limit as x goes to negative infinity in the denominator, we would also get a positive infinity. So we're still getting these indeterminate forms here that are not telling us anything about the value of the limit. So we want to come in and approach this the same way we did our previous rational functions, where we come in and we divide by the highest power of x that we see in the denominator. But in the denominator, we have this square root with the x squared. So in order for us to come in and do that, we are going to consider what the square root of x squared is equal to. But when the limit as x is approaching positive infinity, we will need to consider, well, what is it equal to when x is greater than 0, when x is positive? On the other hand, when x approaches negative infinity, we need to know, well, what is the square root of x squared equal to when x is less than 0? Well, when x is greater than 0, the square root of x squared is equal to x. So we would come in and we would divide everything in this limit by x. So I'm going to come in and I'm going to divide the numerator by x, and I'm also going to divide the denominator by x. But when I divide the denominator by x, instead of writing divide by x, I'm going to write dividing by the square root of x squared, because those are the same thing. And it will make it easier for us to simplify the denominator. Because since I chose to write them with both having square roots, I can combine them all under the same square root. Now I can simplify. We have some things that will cancel here. And now we can apply our theorem that tells us what happens when we have a limit as x approaches infinity of a constant over a variable with a positive exponent on it. So this 2 over x will go to 0, and this 1 over x squared will also go to 0, leaving us with 3 over the square root of 2. Now, on the other hand, as x approaches negative infinity, when x is less than 0, the square root of x squared is equal to negative x. So we're going to come in and we're going to divide everything in this limit by negative x. So I've taken the numerator and divided each term by negative x. And in the denominator, I'm also going to come and divide each term by negative x. So I'm going to do the same trick here, where instead of writing negative x, I just put the square root of x squared, because they are the same thing, and that allows us to do some algebra and manipulate the denominator so that it looks like only one square root is in the denominator. So basically we take this x squared and push it into the square root in the numerator with the operation of division. So now we have some things that will cancel here. And then we can apply our theorem that will send the 2 over x and the 1 over x squared to 0. And I think I dropped the negative sign. I did from back here, that minus x. I should have had that minus sign in here, and I also should have had that minus sign in front of that 3. So go ahead and pick that back up if you drop that with me. That should still be there. So I'm going to go ahead and send these 2 to 0 because they have that x in the denominator, and we are left with a negative 3 divided by the square root of 2. We can confirm our answers for example 4 by looking at a graph of our function. We can see that as x increases without bound, the function is approaching a positive 3 divided by the square root of 2, and as x decreases without bound, the function is approaching a negative 3 divided by the square root of 2. I will mention that it's not wrong at all to go ahead and rationalize those answers and write them as so. Now we're going to shift our focus to evaluating limits at infinity of polynomials. So things like example 5, where we have, instead of a rational function, which is a polynomial divided by a polynomial, now just a simple polynomial. And when we're evaluating these limits, what's most important to us is the leading term of the polynomial. We have to pay attention to the parity of the degree. So the highest exponent from that leading term, is it even or odd? That's what parity means. And we also have to pay attention to the sign of the leading coefficient. Is it positive or is it negative? So let's say that we have an even degree with a leading coefficient that is positive. Well, that is something like x squared, which we know looks like this. And we can see on the graph of x squared that as x goes to positive infinity, as x increases without bound, and I'm just going to write f of x here to keep this general. As x goes to positive infinity, all the way to the right of the graph, as x increases without bound, this limit goes to positive infinity because that graph is shooting up. Similarly, as x goes to negative infinity, as x decreases without bound off to the left of the function, the graph is also shooting up to positive infinity. But what happens if we make the leading coefficient negative? Well, our knowledge of pre-calculus tells us that a negative leading coefficient is going to reflect the graph over the x-axis to now where both ends of the graph point downward, meaning that the limit as x approaches positive infinity and the limit as x approaches negative infinity will both be negative infinity. What is the graph doing as x gets really, really, really big? The graph is shooting down and getting very negative. And it's doing the same thing as x gets very, very small to the left of the graph. Now let's consider what happens if we have an odd degree with a positive leading coefficient. So that would be something like, say, x cubed. We learned in pre-calculus that the graph of the cubic function looks like this. From this graph, we can see that as x increases without bound, as x goes off to positive infinity, as we go off to the graph on the right, it shoots up to positive infinity. On the other hand, as x decreases without bound, as x gets very, very small, as we go off to the left of the graph, it shoots down to negative infinity. But what happens if we were to change the sign of the leading coefficient and make it negative? Well, that flips the graph over the x-axis to where it now looks like this. Now, as x increases without bound and goes off to positive infinity, the graph is shooting down to negative infinity. And as x decreases without bound and we go all the way off to the left of the function and x gets very, very small, the function is shooting up to positive infinity. These four scenarios summarize what situation could be going on when we are looking for a limit at infinity of a polynomial function. Notice that in either one of these cases, the limit does not exist. None of these limits exist because all of these are positive infinity or negative infinity. But we will go ahead and say what the answer is based on this table. With this in mind, let's look at example 5a and b. In example 5a, we're taking the limit as x approaches negative infinity of a polynomial. We need to identify the leading term of that polynomial. That leading term has a positive coefficient of 2 and its degree is even. because the highest exponent of 4 is even. Positive and even looks like this. Looks just like x squared. What is happening as x goes to negative infinity off to the left? The graph is shooting up to positive infinity. In example 5b, the leading term is negative and odd. That looks like negative x cubed, and we're interested in the limit as x approaches positive infinity. So what's happening to this graph as x goes off to the right? It is shooting down to negative infinity.